talk about today?
What are you-
Well, we're going to continue our discussion from last time, but we're going to define derivatives and we're going to prove something about Taylor series. If we have time, then I hope to move on to tangents to things that are not quite functions. And maybe we should prove the product rule and the chain rule and the quotient rule at some point.
Yeah, maybe we should.
Maybe we should. So let me just remind you of some of the things that we discussed last time, and that can orient us. You don't want to be on camera, buddy?
It's completely fine.
I like seeing your face.
So,
So
isn't the definition of a derivative what the second line of that truncation thing, the thing we were talking about in truncations?
exactly correct. And
Definition of a
we're
derivative.
going to see that definition from a bunch of different perspectives, and we'll be able to put it all together in a way that zips up very nicely. Okay, so let me just remind you that the vector space of polynomials of degree
N.
at most, they can be less than n, at most n.
Oh, because the leading terms could be 0.
Yes, have two important bases.
They had 8 important properties.
Sorry, buddy?
They had 8 important properties.
You mean 9 important properties that make them a vector space? Because we start at 0? I think you're muted, buddy. Anyway, the vector space properties aren't that important because we already know how to multiply and add
I'm not
polynomials.
muted.
Oh, now I can hear you. Okay, so they have two bases. One, x squared, all the way up to x to the n. And another basis, what's the other one?
The Taylor basis.
The Taylor basis, x minus r squared, all the way up to x minus r to the n.
Just define it in a. I like my favorite Taylor basis is either where r equals 1 or minus 1.
Those are nice. These are nice, but the power of calculus is it lets us look anywhere at the polynomial, right? Wherever we need to look. And so the fundamental problem, if we have k from 0 to n.
I don't know the quotient rule. Can you give me a bit of a reminder of what it is?
We will prove it after we do the product rule and the chain rule.
Let me know what it is.
How about I show you how we're going to prove it once we have the product rule and the chain rule, and then later we'll prove them. So I'll just do that right now.
I need the product rule since products are opposite of quotient.
I'm going to do it the classical way, and then later we'll see how to do it the algebraic way. Okay, let me just remind you of the classical version.
Do you know anything about the difference rule? You know what happens when you have two functions that are being subtracted?
The derivative just distributes
added,
over
but
it.
not subtracted.
Well, we'll see that. When we get a good definition of the derivative, it'll make it very easy to prove all of these properties. But
the one when you have things that are being subtracted.
The way that I'm going to think of this is I'm going to think of it as u of x times the inverse of v of x.
Okay.
And then when we do the...
Wait, you're not sharing your screen.
Oh, I'm so sorry, buddy. That's probably a lot better. So the vector space of polynomials of degree at most n have two important bases, the standard basis and the Taylor basis. The fundamental problem is if we have...
Other bases?
Well, we could pick two different r's, right? We could have...
But other than the standard and Taylor basis, are there other bases?
Yes, there's the Fourier basis. There's all sorts of basis. There's the Bernstein basis, which is actually okay. So let me write the Bernstein basis.
Bernstein basis.
Yep. Here, I'm going to erase these. We'll see the product or the quotient rule later, buddy. Okay.
There can be another basis.
There can be lots of different bases. So this is the standard.
Let me talk about what I'm there. I know there might be a basis that is the one.
Oh, wait, this should be 1 minus t. Sorry. Other way around.
You see what I have on screen?
Is that a basis for an infinite dimensional vector?
No, I accidentally forgot to write the end. It's for a finite dimensional, but I forgot to write the end.
Okay. How is that different from the one that we already have? Oh, it's alternating plus minus, right?
Yeah. But is it a basis?
That would be an interesting question to prove. Some things are really easy to prove that they're a basis. Other things, not so much. But do you see this basis?
What if you multiply a basis by a constant? You get another basis, right?
Yep. Yes. So look, do you see this thing right here?
Yes.
This is called the Bernstein basis. And this is really important as well. We're going to see this later. And then there's one more basis that we should write.
4 alarms for your class.
Oh.
All at the same time.
So we have t to the n, comma, n choose 1 times t to the n minus 1 times 1 minus t. And then n choose 2, t to the n minus 2, 1 minus t squared. Do you know what this basis is?
No, I don't know what it is.
You sure you don't know what this is?
Let me take a close look at the basis. I think that is version 2 of the Bernstein basis.
It's the Pascal basis, right?
I'm like that.
Or some for things that involve.
Why it's called Pascal?
Why?
Because of the parts that are in red.
Well, what's actually the sum of all of these equal to? If we add all of these up, what number do we get?
You mean all the red ones?
Yep. Not the red ones, all of them. T to the n plus n choose 1 times t to the n minus 1 times 1 minus t plus n choose 2 times t to the n minus 2 times 1 minus t squared. T plus
1 minus t. Okay, that's just 1. 1.
Okay, so the Pascal basis, when you make it add up to 1 like this, so this is not quite the Pascal basis, because the Pascal basis would have an a and a b instead of a t and a 1 minus t. So instead of a Pascal basis, I'm going to call this the de Castelnau-Bézier.
Did you just make that name up?
Nope. The de Castelnau-Bézier basis. And this is used a lot in computer graphics.
It's just a Pascal space in a special condition.
With a special condition, you're right. But that special condition lets us do a lot of very interesting things, which is why it deserves its own name. But regardless, this is a basis. These are all very important bases for calculus, right? But these are some good examples. So
if t was 1, then it wouldn't work, since everything would just become 0.
No, if t was 1, then this last term would be 1. But you're right that if
0, since 1 minus 1
oh
is
no, then the first term would be 1. But we're not thinking about t being specific values here when we're talking about a basis of a polynomial. So even though you're right that in that situation it would all degenerate, everywhere else it's fine. So
what about if it's -1?
it's fine. It doesn't matter what value of t it is. So when we wanted to answer this question, how do we perform a change of basis? Okay, equals 0 to n.
If you divide the plane by the original basis and multiply it by the new basis. Is that right?
We saw that basically we could rewrite this equation, right? This is what we're trying to do with a Taylor series. And we saw that we could rewrite it as this matrix equation, A0, A1, all the way down to AN is equal to this modified Pascal matrix. I'll write it.
Oh, you mean the inverse of the... Because if I'm going to take a guess here, but if matrix A times matrix B equals matrix C, then I'm going to take a guess that matrix A inverse times matrix B inverse is equal to matrix C inverse.
That's an interesting guess, but it's actually wrong.
How?
I'll show you in just a second. That's a great guess, but it's actually wrong. So let's assume that this...
It would make logical sense.
So let's multiply them like this.
For numbers, that would be true.
It would, but what's the difference between numbers and matrices?
That... Wait, C? Hey.
This would be I, right? Our identity matrix, our one matrix. No, buddy. So this is what it turns out. Let me just spoil the answer for you. So if A, B equals C, then C inverse is equal to B inverse A inverse. So
wait, is B inverse A inverse also equal to C?
No.
No,
it's equal to C inverse.
No, is it B inverse A inverse equal to C inverse? Can you reverse the equality?
Yes. The equalities are reversible by definition.
Okay, but it just looks nice because it's all backward.
So let's call this matrix U inverse, and we saw that the ijth component of U inverse is -1 to the ith power of j.
You forgot -1 to the jth power as well, so I plus j, actually. There'd be an I plus j or something.
I see what you're saying, because this definition right here would have all of the columns be the same sign. This is what it is. Okay, and we saw that if we define U inverse this way, then using Lagrange's...
What would L inverse be?
Actually, I lied. There's a mistake here. This is for R equals 1, right? Let's rewrite this. Let's rewrite this for a general R.
R not equal to 1.
Let me rewrite this.
So R cannot be equal to 1.
So we had -R, R squared minus... So R can be anything. R could be 1, but we want R to be able to be...
R cannot be 1. It just can't be 1.
Why are you saying it can't be 1?
Because it can't. It just can't. Otherwise, it would break math.
It won't break math.
If it's equal to 1, it won't break math.
If it's equal to 1, it will not break math. All right. So then we had a 1 here, a minus 2r, a 3r squared, a minus 4r cubed.
Zeros are actually zeros. R could be anything. R could even be irrational.
R could even be irrational. That's 100% correct.
Wait, if R is irrational, then how do you know if those things are still zeros?
Because these zeros correspond to powers of x in the basis. So it has nothing to do with the irrationality. All right, and then we have B0, B1, all the way up to Bn. So let's call this U of R to the n, and we saw that the ijth component was equal to minus r to the ijth power, right? I plus jth power times j choose I. And this was the inverse, so I'm going to put a minus n there. I should put a... We don't need an n there. We'll just put a minus 1 there. So then we saw that by Lagrange's...
Wait, is the minus n trying to correspond to minus 1 times n?
Yeah, but n is actually not a power of u, it's the dimension. So that's why I decided to not write the n, because the dimension should just be implied.
Idea. Why don't we put n here?
Maybe, but it's a lot of numbers that we don't really need. So this we saw was r to the I plus jth power times j choose I. Okay.
What's the r there for?
The r is going up by powers, right?
Oh, yeah. That's what, like, if r, that's what.
It's not I plus j though. It's not I plus j.
It's I minus j.
You think it's I minus j?
Yeah. If it's not plus, then what would form this alternating pattern other than minus?
Well, look, we could have a minus 1 to the I plus j, but the powers of r do not behave that way.
And then do r to the I plus j.
To the I plus j, that's not correct though, because look,
Oh, just keep r.
it should be I plus j minus something, or a product.
Wait, you know how this is 2, even though their I is 1 and their j is 3? I think it's minus. No, I think it's I minus j. Something's convincing me that it is I minus.
No, it's so n rows. It's row by column, so it's j minus I. It's j minus I.
It's j minus.
Because j is the column that you're in, right?
Yeah.
So if you're in the third column,
Wait,
it's
that's the fourth column.
No, j minus I. Well, no, it starts from 0.
Oh, I thought it started at 1.
So we can have minus r to the j plus I, right? Does that work? J minus I. All right, so by Lagrange's translation trick, we get these matrices. So with these matrices, now that we can do the change of basis, I'm going to define something. So we're going to have a bunch of definitions, but we know that f of x plus r is equal to the sum from I equals, so this is not a definition. This is Lagrange's translation trick that we're going to do this again, and it's going to motivate our definitions. But this is what we saw last time.
Hey, who's Lagrange?
Lagrange,
Actually invent this thing?
yes, in his 1797 paper, he wrote a paper in 1797 about it. Okay, so we have this is aix plus r to the I, but then we saw that it can be rewritten this way: I equals 0 to n of, in parentheses, j equals I to n of ai, ji, r to the j minus I.
Just say AI.
Yeah, I keep saying that. So
Oh my goodness.
here is one thing to note. The binomial theorem is symmetrical, right?
Yeah, because wait. Yeah, it's because there's an A plus C in the thing, and then if you make it C plus A, it doesn't really make a difference.
Oh, what happened? Oh, all right.
You started a new page.
All right, I got back. So by symmetry, we can also write it this way. This is a really important fact that it can be written in two different ways. And sometimes you want to write it in one way, sometimes you want to write it in the other to make it easier to prove theorems. So this time we put the x on the inside and the r on the outside. Okay? See I did this swap? Okay, so the symmetry of the binomial theorem is what is letting us do this. This is one of the key formulas. So I would appreciate it if you wrote this formula down, because it's going to be
Wait a minute. Is there anyone in the waiting room?
I don't think so.
You can see who's in the waiting room, right?
Yep.
Is
it says
anyone?
No, Matt's not here. Matt told me he couldn't make it today. All right, so have you ever heard the term different? Okay. So with this, let's define the truncations of f of x plus r. So the kth truncation of f of x plus r, we're going to define it this way. It's going to be the sum from I equals 0 to k now, because we want the top degree to be k, of the same coefficients. So j equals I to n, ai, j choose I, r to the j minus I, times x to the I. Okay, but sometimes we're going to want to, so this is for if the r is fixed and the x varies. But sometimes we're going to want x to be fixed and r to be varied.
Then you can just reverse everything.
So I'm going to write tk, but I'm going to put an r in parentheses here. F of x plus r is going to be the sum from I equals 0 to k of the sum from j equals 1 to n, ai, j choose I, x to the j minus I times r to the I. Okay, so if I put an r in parentheses on the k, what that means is write it with x fixed and r varies.
And what if you want both of them to vary?
Then it doesn't really matter which way we write it, but it's going to make it.
One of them has to be fixed if you write it either of these ways.
Yeah. So
then how do you make both vary?
If you think of both of them are varied, then it doesn't matter which way you write it, because well, you're not going to be able to truncate it in the same way, though, if you think of both of them are varying. But we won't need to do that. It's just important to know that we could have either of them be moving and either of them be fixed, and they mean different things.
Which one do you want moving and which one do you want fixed?
Well, for our definition of a differential, so let's define a differential.
I know when a derivative is taken as, like, if a derivative of A is taken of a expression in A and B, then B will be regarded as constant.
Okay, so I'm going to say that d0 of f is just equal to f of x.
Okay.
But this is lowercase d for differential.
Wait, what is the d negative one then?
Great question. You can think of that as an antiderivative, but that's skipping way into the future. For now, we're only going to focus on natural numbers, okay? So the kth differential of f is...
Mr. Corbin, do you think 0 is natural?
Yes. I think 0 is natural because I want to have an identity element for addition. I want to be able to add something and nothing happens.
Yeah.
Okay, so the kth differential of f is going to be the k plus, the kth truncation in r. So we're thinking of r as fixed and x is varying, minus the k minus 1th truncation at r, f of x plus r, right? So let's look at some examples of this and try to understand what it means when k is equal to 1. Okay, so let's look at this example. F of x is equal to ax cubed plus, or let's do it the other way around actually. A plus bx plus cx squared plus dx cubed. So what is d1 of f? All right, so that's going to be t1 in r of f minus t0 in r of f. So that's going to be equal to, I'm just going to skip some of the work. That's going to be a plus bx plus cx squared plus dx cubed plus, in parentheses, b plus cx plus 2cx, b plus 2cx plus 3dx squared times r, and then minus a plus bx plus cx squared plus dx cubed. All right, so then what I'm going to look at on the graph, and this thing is just equal to b plus 2cx plus 3dx squared times r, right? So let's say this is our graph, and I take 2 points. This is going to be the point x comma t0 at r of f, and then this point right here is going to be x plus r t0 of r, t1. Yeah, t1 is what we want. F of x plus r. So for a fixed r.
Yeah, and then a fixed x would be similar.
Yeah, this will be fixed x. So let me just show you what I mean. I'm going to use capital X for fixed x, but let's do this in GeoGebra, because I want us to notice something about this function. So new share, GeoGebra Classic. Let's get some variables going. A, B, C, D. And we're going to need not an E. We're going to need a capital X.
You put A, B, C, and D. It's recommending E.
And then we're going to need an R. Okay, so we have A plus B x plus C x squared plus dx cubed. Cancel, that's not equal to f. Okay. F of x. Okay, and we want the point that's going to be capital X comma f of capital X. And then we're going to want to make the point capital X plus R plus T1 of X plus R. So that's going to be f of capital X plus, in parentheses, B plus 2.
Hold up, I'll have to go. I'll be right back.
Okay.
I'm back.
All right, Ian. So this is our function. And so let's talk about what points we have. Text. So we have the point big X comma f of big X, right? And then we have the point big X plus R comma T upper 1 lowercase, in parentheses we have an R of f evaluated at X. Okay. So let's make these a little bit bigger because I want you to be able to see these formulas on the same screen. Please give me this. All right. There's a very important observation I want you to make here.
What's that observation?
Okay, so this is, here, let's say this is point A is equal to this. And point B is equal to this, right? On our screen. Can you see A and B? I'll put our sliders over here. Okay, so big X, we're just thinking of X as our spot on the graph. And we have A is just a point on the graph. One thing is that B is not on the graph, right? As we move x around.
Be on the graph.
Well, what happens when r gets smaller? When r is 0, then it's on the graph, right? So let's hold it here and let's have r move back and forth. What happens to B?
It goes in a line.
It goes in a line. Let me turn on the trace of this line. What line is that? It's the tangent line. So
you make the line blue so it's easier.
How about I make this vector right here blue, the vector between A and B?
Maybe you could do that.
That will be blue. Okay, and then let's turn off the trace of B. All right, so as we move x along the function, we see that the difference between A and B is the tangent vector, right?
There's a random point.
That's from the trace earlier, sorry. And what we see as we change r is telling us like basically the size.
Multiply the blue vector by.
Yeah. So what is the components of the blue vector? So let me write this again. So let's say v is equal to b minus a.
I think GeoGebra already gave it a name.
Yeah, they called it u, but we're going to think of it as v, okay?
I prefer calling it u because it's already called u.
All right, fair, you win. Okay. Large. So we have this.
Vectors.
But if we look at the components, it's x plus r minus x, comma.
Wait a minute, that's just r.
It's just r. It's just r. I want you to hold on to that thought real quick. And let's also. I just want to make it look good. T1 F underscore in parentheses. We have R F of X plus R minus F of X. And then that's equal to, in parentheses, R comma D underscore 1 of F evaluated of F of X. There you go. Okay, so what we can see then is that if we divide the differential by how much we're actually stretching out our change, right? How much we're actually changing our function by, then we get the slope of the tangent line. So since we care about slopes, that sort of tells us that we should think of the differential as being like the slope of the tangent line, basically, or related to the slope. So do you see how the differential is appearing in this situation, though? That's what I did this equation in blue for.
The equation is in blue because the vector is in blue.
Yes, actually, can I get you to write down this equation for me?
Sure. Okay. I'll tell you when I'm done.
Okay.
U multiply by. Can I just write r on the x coordinate?
Yeah.
Because r and then truncation 1 is r.
So after you're done writing that down, I guess. Oh, wait.
X plus minus x, which is equal to r, comma. I like using the first derivative as d.
Well, I'm going to use different notation than what you've seen. We're going to use lowercase d for differential and uppercase d for the derivative proper.
So
You'll see why later.
Differential and the
So the differential, the first
I just do
differential.
D if there's a 1 there.
Wait, buddy. So the first differential is the linear change in the function for a fixed r.
Differential I just write as D.
Okay. I want you to put a 1 because the second differential is the quadratic change.
No, the second differential I write as D2, the third I write as D3, and so on.
Okay, great. So let's go back to OneNote.
D for the first.
Let's go back to OneNote. And so we're going to define first the 0th derivative
The 0th derivative
of f. We're going to use capital D.
Just f.
It's just f of x. Okay.
Why do I keep thinking the 0th derivative is 1?
The kth derivative.
Mr. Corbin?
Yep.
The 0th derivative, I keep thinking it's 1 for some reason.
Not quite. The kth derivative of f. Tk of f. We're gonna say that is tk at r of f of x plus r minus tk minus 1 of r f of x plus r, and this time we're going to divide by r to the kth power.
Okay.
So one thing that you should notice is that this is actually equal to dk of f divided by r to the k. And so d1 of f is equal to the slope of the tangent line. At x.
Yes, okay.
Capital X, fixed x, right? But that's just...
Capital X means fixed x?
Yep. So what are we thinking?
Just put x0 for fixed x.
Okay, so buddy, sometimes...
Wait, hold up, I can't see the bottom.
Oh, sorry. Sometimes r is called dx.
R is called d multiplied by x?
Dx, the differential of x, right?
Yeah.
Actually...
dx? Is it the first differential?
Yeah, so I'm actually going to make some changes. I'm going to put the definition, the index, the 0, and the k, I'm going to put those on top. This is going to make...
Yeah, but just keep the d for 1.
Yep.
It just saves some time.
We're going to put the 0 and the k here.
0 and the k there? Okay. Wait, the k...
Because what does this formula become? What does this formula become right here if we write r as equal to dx? So if r is equal to dx, then we get the kth algebraic derivative of f is equal to the kth differential of f divided by the kth power of dx. But I like to use the r because this is dk over f over dx to the kth power is not equal to the calculus operator dk dx to the k f.
Oh, so you want it equal to the calculus operator?
It's not quite equal to it. What it is equal to, what it's equal to is actually this. That's why I'm being careful with the parentheses, right? That's why I prefer to write an R on the bottom, because it is a little bit different from the classical one that you learn in standard calculus class. But in standard calculus class, they're defining that by a limit, right?
It also looks like d times x.
Yeah, it kind of does, but sometimes we just have to put up with notation like that.
if you define D as something.
So can I want to define now, I want to rewrite D1 of F as a matrix product. So we, let's actually see what dk, what is dk of x to the nth power? Well, what that is that's the kth truncation evaluated at r of x plus r to the nth power minus the k minus 1th truncation evaluated at r of x plus r to the nth power, right? So let's expand this out. That's going to be the sum from I equals 0 to k of n choose I x to the ith power r to the j minus ith power, or to the n minus ith power, sorry, minus the sum from I equals 0 to k minus 1 of n choose I x to the ith power r to the n minus ith power. So what does this simplify to, buddy? This actually has a really easy simplification.
It's equal to the value of, it's equal to n choose k times x to the k times r to the n minus.
I actually lied. This thing needs to be written with r fixed, right? So it should be rx this way. Rx.
Then it's r to the k times x to the n minus k, because the sum, because this sum, hold up, let me show you. This sum cancels with most of the part of this sum, and then this treats it like they were expanded, and then the blue part would be just that.
Great. So what this implies for us as well is that what is d of 0? dk of 0. Well, that's going to be equal to dk. Well, no, actually, let's do it this way first. What is the kth derivative of a times f of x plus b times g of x?
Yeah.
Well, let's use our definition that we just had here. So this is where we're going to close it off. We're going to learn how to write this as a matrix, and then I'll see you next time. Okay, buddy? So this is equal to, so we're doing all of it divided by r to the k. We're going to have the sum from I equals 0 to k of, actually, we can just do it this way. We're going to have t r ith kth power of a f of x plus r, and then minus the k minus 1th truncation of a f of x plus r. And then beneath that, we're going to have a plus b times g of x plus r minus t, the truncation k minus 1 b of g of x plus r. Actually, I skipped a step. My apologies. Let me rewrite this. The step that I skipped is, this is tk af. I'm going to suppress the x plus r now. No, I shouldn't do that. Let me write this correctly. It needs to come out correct. Plus b times g of x plus r minus t. Oh, and this should be at the rth one. There's so many things to write. G of x plus r All right, so first thing that we can do is the truncation actually doesn't care about plus signs. It just distributes over plus signs.
And what does it do with minus signs?
Plus signs, minus signs, we're going to see that it doesn't matter. As soon as we see how it works with A and B. So we have A f of x plus r minus tr k minus 1 a f of x plus r. So this is what I wrote last time. tr k b of g of x plus r minus t of r k minus 1 b g of x plus r. All right, but the thing about this a is we could multiply our sum by a before or after we chop off the terms. It's not going to change it. So we can actually rewrite this.
Yeah, that makes logical sense that it won't change.
We can pull the a to the outside. X plus r minus tk minus 1 of r f of x plus r plus b times on the outside trk g of x plus r minus t of r k minus 1 g of x plus r all over r to the k. But this is just equal to a times the kth derivative of f plus b times the kth derivative of g, right? So what that means is that derivatives have a distributive law.
I knew the distributive law of derivatives before, but I
Yeah.
don't know how to prove it.
Well, this is a very nice proof, but it only works for polynomials right now. But the proof is exactly the same with the difference quotient. So derivatives have a distributive law, and what we can see is that if I take the derivative of 0, that's the same thing as the kth derivative of 0 times x to the 0, right?
0x to the 0, that's just...
Or I could just write to the n. It doesn't matter. We can write to the n. It doesn't matter. This is equal to 0 times the kth derivative of x to the n, but that doesn't matter. That's just equal to 0, right?
So 0 times anything is 0. So why
since we have that dk of f plus g is equal to dk of f plus dk of g, and d0 of dk of 0 is equal to 0. That means that dk of f can be written as a matrix. All right, so let's see an example. So using the fact that dk of x to the n is equal to... Wait, before we do this, actually, let's prove a theorem. Let's prove the most powerful theorem of the night. This is going to be the theorem of the night that is going to be really good. We still need these. What is the kth derivative? We also said that dk of x to the n was equal to n choose k r to the... Oh no, we factored out the r, so there's no r. The r is factored out in this thing. So we had to divide this by r to the k, right? Divide by r to the k. So then there's no r to the k in this thing because we're dividing by it in the derivative. That would be the differential if it had the r in it, right? So I'll write this here in red. We have that dk of x to the n is equal to n choose k times x to the n minus k times r to the k. But down here, since we have that the derivative of x to the n is equal to n choose k times n minus k, then we have this new theorem. If f of x is equal to the sum from I equals 0 to n of ai x to the I, then dk of f of x is equal to the sum from I equals 0 to n of, that's going to be di of f evaluated at r times x minus r to the ith power. And this is called the, oh, wait. No. We just want this one. No kth derivative. This one. This is called the Taylor series at r.
Yeah. So the Taylor series at r.
How do we prove this?
What would the Taylor series at r plus 1 mean?
How do we prove this?
Wait, I'm asking the question.
If we plug in r is equal to 1, then we get the Taylor series at 1.
No, the Taylor series at r plus 1.
You just have to plug in r plus 1 for r.
Oh.
Let's prove this. This is a theorem. The proof is really nice. So recall that di f of r, I'm going to write this as the kth truncation in f of x plus r. So there's no r on the bottom, which means that r is varying and x is fixed. Minus t to the k minus 1 f of x plus r. All right, so what happens if we sum from I equals 0 to n of di f of r, and then we have x minus r to the ith power. So that's going to be equal to t0 is the first one, right, of f of x plus r. Divided by r to the 0, which is just 1, plus t1 f of, let me prove an easier formula, actually. This will be...
Easier formula take us to the main formula?
Yeah. If I prove this other one first, it's going to make our lives a lot easier, though. All right, so let's prove some things first. The kth derivative of f of x at this point is going to be the sum from I equals 0 to n of, that's going to be, so we're going to take the derivative of this. Everything that has everything that has an index less than k is going to turn into 0 when we take the derivative eventually, right? So the I actually has to start from k here.
Stuff with index more than k.
Index more than k are the ones that are not going to be 0 automatically. So those are the ones that we want to take care of.
So those are the ones that are going to survive?
Yep. So that's why our new sum starts at k, I equals k.
You know how I would like to think of it?
How would you like to think of it?
There's a derivative apocalypse, and the only way to survive the derivative apocalypse is to have an index more than k. Otherwise, you'll get wiped out by the derivative apocalypse.
Yep. All right. So you see this thing, this definition, that just follows from what we knew about how it distributes, right? Plus how it acts on our basis vector, our basis polynomial x to the n. So we only needed to know how the derivative acted on our basis to figure out how it acted on everything in the vector space. That's the
Yeah,
power.
because the basis is the what defines the vector space. What helps define it.
Yes. So I think actually this is a good place to stop. Next time we will prove Taylor's series formula, but this is a good place to stop, right? We've got a formal definition of the derivative and differential, and then next time we'll be able to prove Taylor's theorem and see how it connects to matrices. So, are we going to chat tomorrow, buddy?
You are depends on if you're available tomorrow.
I am available. I'm asking if you are.
I think I will be available tomorrow.
So then I'll send the email tomorrow, and if you can make it, then you can make it. Okay. All right, buddy. I hope you enjoy the rest of your Sunday afternoon.
Okay, bye. Thank you.
Later.